Okay, it's 15 or 10 already, so let me erase this part and let's continue with our discussion. I said that if you have this kind of a first order system, you can make the implementation of this first order using a feedback kind of loop. This feedback strategy will be very much utilized in your next semester's control systems again. That's a very typical way of doing things. And it also explains a lot of control theory in itself. For instance, suppose that you have one branch of system from X to Y, okay, the top branch. And the branch is an integrator, as you see, it's accumulating. There's a 1 over S, that's an integrator. And it's an unstable system. Where is the pole of 1 over S? The pole is at S is equal to 0. And therefore, to the right of 0 will be your region of convergence, and it will not include the j omega axis. So the integrator is an unstable system. By putting this kind of a feedback, a negative feedback, why? Because the coefficient here is a negative one, or we subtract some amount of output from the input, and by putting this feedback, the overall system response automatically becomes 1 over S plus 3, which now has a pole at -3, and to the right of -3 includes the j omega axis, so the system becomes stable. So feedbacks, negative feedbacks like this one, will tend to stabilize the system. A question, again, that comes to my mind is to give you an unstable system here and put a feedback and leave this value to be equal to A, okay, a coefficient A, and ask you the following. Two parts of a question. First, find h of s in terms of A. So A will be inside the denominator somewhere, maybe. And part B of the question is, what is the range of A that stabilizes the system, makes this a stable system? So A should be in such a way that the new pole should be to the left of the j omega axis. For example, if the question is originally like this form and I put an A here, then the answer to that kind of a question would be, the answer is A is less than 0. If inside this box, I say A. This is the range of values which stabilizes the system. The answer is therefore A is less than 0 in that case. Anyway, you will have to deal with these things in control systems theory. So I'm just briefly mentioning about these things. And the next example is again a first order system, but now it has some zeros as well. H of S is equal to S plus 2 over S plus 3, for example. So there's a 0 at -2, and there's a pole at -3. The way to approach this kind of a thing is, unfortunately, according to the book by Oppenheim, not relating much with the numerator. So we don't really care with the numerator. We just say that the numerator is has nothing to do with the integrators of the denominator part, and we simply say it like there is an S plus 2 times 1 over S plus 3
Hocam sesiniz gitti de.
Sorry for this inconvenience. Okay. It's not only the sound that went away, it's everything. So I started screen sharing again. Okay, so it was just a kick out situation. So yeah, it's not only the sound that went away, it was everything. What I was saying is the numerator part, we don't care. we just say that the system is consisting of a further numerator system, which is s plus 2. The thing is the denominator part that we are trying to implement using a feedback. Sorry. So let us change the color first and continue with the second order examples. They will be more a little bit more interesting. H of s is equal to 1 over s plus 1, s plus 2. This is a second order system with two poles. There are two other alternatives of this. It could be 1 over s plus 1 minus 1 over s plus 2. Could be written like this, or it could also be written as 1 over s squared plus 3s plus 2. So all these things will be equal to one another. But how are we gonna realize these things using system blocks of integrators? I'm going to say that there are these three different equal approaches will correspond to three different realization forms: 1, 2, and 3. Let's call it this way. So let's do now realization number 1. The realization number 1, it's maybe the simplest because it's consisting of two cascaded first order systems. One of them is 1 over s plus 1, the other one is 1 over s plus 2, and we multiply them. So there is h1 and h2. h1 is 1 over s plus 1, h2 is 1 over s plus 2, cascaded in the Laplace domain. So we have an x going into a first order system whose implementation we know from our previous experience to be like this. This is 1 over s plus 1. I finished. And then the next system that comes afterwards is 1 over s plus 2, which is also another first order system. And its implementation is this. And the output is y. This kind of an implementation could be named as a cascade implementation. All right. And it's alternative number one for a second order system. The second alternative is for the region red marked as 2. So let's also do it. 2. We have again two first order systems. One of them is 1 over s plus 1, and then we also have 1 over s plus 2, and we subtract the second system output from the first system output, and it may go like this. This is 1 over s plus 1. Okay, the input is x, the output is the output of 1 over s plus 1 with the same input. And now I take one branch from the same x and implement 1 over s plus 2. Like this. And now I subtract the output of the second, the lower system, from the upper one by putting a minus sign here. Okay, so the output of 1 over s plus 2 is multiplied, subtracted from the output of 1 over s plus 1 system. And this is the new implementation. It's an alternative way of implementing the same system. And this implementation we can call a parallel implementation. Okay. And the third one, which is this. Now it looks a little bit complicated. I may want to copy the equation again to the new page because I don't want to scroll up and down all the time. So let me write the h of s again, so that I won't have to copy. That is 1 over s squared plus 3s plus 2. This was it. Okay. Now, how can I make this kind of an implementation without a cascade form or a parallel form? It would be named, by the way, direct implementation, direct form implementation. This is equal to y of s over x of s, and it makes s squared y of s plus 3s y of s plus 2 is equal to x of s. I have to, unfortunately, elaborate a little bit on this one for the implementation. And it makes, I want to isolate the highest power of s term at the left-hand side of the equation. And that makes y of s is equal to 1 over s squared x of s. But I have forgotten the 2y of s here. I'm sorry. And minus 2 times 1 over s squared y of s minus 3 times s over s only of y of s. So this is the implementation that I will try to make. And the realization, the direct form realization, you have to be very careful about looking at what I'm doing here, because you may have to do something similar to that. So please take care of my philosophy or my approach to this, the solution of this problem. We have a y of s at the output. Now I have to multiply y of s by minus 2, and I will have to accumulate this. So it will be added to what? Now that's a question. That's difficult thing that I'm trying to do here. We have an input x, by the way, and x goes into the integrators actually twice. Why? Because as you see, there's a 1 over s squared times x of s. Of course, there are other components as well, but x of s is integrated twice. So there's a 1 over s system, and its output also goes to another 1 over s system to contribute to y. But there are, of course, other components that needs to be added onto x. X is itself is not only integrated twice. There are other things. For example, y of s times minus 2 here, minus 2 times y of s is also integrated twice, 1 over s squared. So I am supposed to have that to be equally integrated twice. But there is also a minus 3 times 1 over s times y of s. So this thing is not integrated twice, but it must be integrated only once. So I'm going to open a branch from here, minus 3, put it here, and now it will be something else. So what is that thing? Why am I putting it there, and what it really corresponds to? Notice that the output here is y. Therefore, this point is a point which, when I multiply with 1 over s, or when I pass through 1 over s, it makes y. So this point is s times y. So this point is s times y of s. That is the signal that we have there. And s times y of s, now let us watch what is happening to s times y of s. S times y of s is multiplied by minus 3. Meanwhile, I'm going to write it. Minus 3 times s times y of s comes here. And then it is added to x and other components. It's added once here, but I'm isolatedly thinking of s times y of s. What's happening to it? It's multiplied by minus 3. Then it passes through 1 over s here. And then it passes through another 1 over s because before it reaches to y times 1 over s. And what does that make? This s and this 1 over s, one of them cancels. It becomes minus 3 times 1 over s y of s, which is exactly the same as this one, by the way. Okay. So it works. I made it magically, like it was like magic, really. But if you solve sufficiently many direct implementations of such second order, maybe third order systems, so please try to extend this polynomial, the denominator polynomial, into a third order polynomial, and try to come up with a direct form implementation of that. Then you start making some observations. For instance, the last 2 comes as minus 2 here, and the one before that comes as minus 3, and the one before that will come as minus of whatever that coefficient was, etc. And this is the structure that you need to make. Have intermediate downward going branches from top to bottom. So you will learn how to make these things in an automatic way. But this is the third and the last way of having a second order realization. So we have cascaded things, which is the best, but for my purposes, it just works perfectly. The first implementation, the top one, just first order systems coming one after another in the form of multiplication. And the other one is in the form of a summation. So we split into parallel first order forms and then combine them. Realization number 2. And the third realization is the direct way of realizing these things. Okay. Now, that essentially concludes the discussion about the normal Laplace transform according to our book. But I may put some examples without solutions to give you an idea about, hint about what could be asked. For example, there may be an input and there may be some boxes here. Sorry. Let's put 2 here. And here, let's put a -1. Here, a 3. And yeah, that's it. Maybe we may put another box here, but let me not do it. This is why. Now, this looks a little bit more complicated than what we have seen as examples of first order and second order systems, etc. By the way, this is a second order system. It must be, because there are 2 1/s's, which makes it a second order system. But nevertheless, there's in some place there's a feedback from the intermediate place with a value of A, and the question is, what is the range of A that makes this causal system, I'm telling that it's causal system, stable? So for what values of A is the system stable, if it could ever be? So the answers or the answer candidates, it may be a test question, for example, is A, the set is the empty set, one of them. There can be no real A. It must be real because imaginary values will not contribute to the stability. There's no real value A that can be found that stabilizes the system, an empty set. Another could be A could be between some value and some other value. It could be less than from some value. It could be more than from some value. And it could also be just the whole real values. Every real value will stabilize, make this stable. So I gave you 5 options, for instance. So this is a very probable candidate question that can be asked regarding these topics. What's the range of A that stabilizes? You have to find the correct thing. But for that, your job is to find this system as H of S. So what is this H of S from X to Y? In between there is a system. What is this H of S? And where are the poles of it in terms of A? So those poles must all be at the left-hand plane so that the j omega axis is included in the region of convergence. That is the stability condition. So what A values will do that? A more enjoyable but not so easy question, maybe I may replace this 3 by -A. I put a over there and minus a over there, so it will be a very enjoyable question of h of s in the denominator will contain a function of a. So what are the roots of those, and how can you guarantee that all the roots of the denominator are negative? What could be a for those? Right? Not very easy questions, but good ones nonetheless. Okay. Now, that essentially concludes the so-called bilateral Laplace transform. But there is also so-called unilateral Laplace transform. And what is it? That unilateral Laplace transform is the more commonly encountered Laplace transform, where the integration starts from zero plus actually, just a little bit above the 0 point. And I tend to indicate it as x sub u, just to indicate that it's the unilateral Laplace transform, whereas capital X by itself would correspond to the Laplace transform. So x sub u of s is the unilateral Laplace transform of x of t. And the definition here is, it's not 0 plus actually, it must include 0. So sorry about this, it's from 0 minus. This 0 point must be included to infinity, and the rest is the same, x of t e to the minus st dt. This is, by definition, different from an integral from minus infinity to infinity. And it will give you different results. Let me give you an example about that. But I can say that, let me write it in red, as long as x of t is equal to a function times u of t. So if x of t includes a term called u of t in the multiplication form, then x sub u of s will be equal to x of s, because the signal itself will start from 0. So the integral will also start from 0 and nothing will change. But if the signal contains, if x of t contains some coefficient, some information at the negative time instances, if it starts earlier than 0, then of course things tend to become problematic, different at least. It's not a problem. This is still a perfectly fine definition of the Laplace transform, but it requires further information. The bilateral, the normal Laplace transform requires the knowledge of x of s as well as the region of convergence. You remember that? The xu does not require the knowledge of the region of convergence, because it's always to the right-hand side, so it's always to the right of the rightmost pole. Causal signals are implicitly assumed, and we don't need to indicate it deliberately. It's always to the right of the rightmost pole. You don't have to indicate it, and there's no alternative inverse Laplace transform or anything. The inverse Laplace transform is unique, even if you don't indicate the region of convergence. So let's think of this x of t, which is an artificially generated t plus 1, u of t plus 1. This is a signal that I have artificially generated by shifting an e to the minus at u of t to the left-hand side a little bit by 1. By 1 unit, 1 time unit, I shift that signal, that famous signal, to the left. And when you find the normal bilateral Laplace transform, you will find x of s to be equal to e to the s over s plus a. And the region of convergence will be real part of s is greater than minus a. S is equal to A is a pole, and to the right of it will be the region of convergence. Now, how about, I didn't do that, but you can always put it inside the formula. And in fact, you don't even need to put it inside the formula. E to the S will be the response of the shifted version. Because if you shift in time, in the Laplace domain, you multiply it by e to the shift amount times s, and shift amount is 1, therefore e to the s times 1 over s plus a will be your result. That is, you can also solve it without really integrating it again, or you can just apply the property, the related property. But let's take a look at what is the unilateral Laplace transform. And that is, let's do it because it's the first time that we are doing e to the minus a t plus 1. U of t plus 1, yeah, let me write it. But that will be quite unnecessary because u of t plus 1 starts from minus 1 anyway. And the integration starts at 0. So along this integration limit, this part is already just equal to 1. E to the minus st is there, dt. In fact, that is the critical thing that makes the difference. Here, in this one, the integration was from minus 1 to infinity, because the signal is from minus 1 to infinity. But here, as you see, the integral now starts at 0. That would give us the difference between the unilateral and the bilateral Laplace transform. And it's from 0 minus to infinity, e to the minus a, because there is an e to the minus a times t plus 1. That plus 1 will give me an e to the a, and e to the minus t in parentheses s plus a dt. So this is the integral that we need to take. This part of the integral is familiar. We know it's equal to 1 over s plus a, the integration will give you. So this will go out of the integral as a coefficient, and the result will be e to the minus a over s plus a, or e to the minus a times 1 over s plus a. Now, as you see, these two are not equal to one another. And furthermore, I don't need to indicate the region of convergence for this last expression. The region of convergence, when you have this, there is a pole. Okay, there is, of course, a region of convergence, but we don't need to indicate it because it's given, deterministic. The pole is at minus a, so the region of convergence is to the right of minus a. That's the automatic region of convergence that we have. In a sense, we can say that I'm not going to give any further specific unilateral Laplace transform evaluation examples, but I will show you something else. We will have to apply these unilateral Laplace transforms to their own particular purpose, which was differential equations. So we will see a little bit of differential equations, but not the unilateral Laplace transform. If we can notate like this, unilateral Laplace transform of x of t is essentially equal to, by the way, this is what I mean by xu of s, is equal to the Laplace transform of x of t times u of t. So I limit my signal by multiplying, by force multiplying with u of t, and then afterwards I take the Laplace transform of it. It becomes the unilateral Laplace transform. It always starts from 0 and goes to the right-hand side. So that is the unilateral Laplace transform. There are a lot of questions that you can solve from the book, but what I want to really focus on now is the following: the application of the unilateral Laplace transform to differential equations. Because in differential equations, without the knowledge of region of convergence, the causality, non-causality, etc. are a little bit ambiguous. With the unilateral Laplace transform, they are clear. It's always causal. But this time, now we come up with something else. The time derivative, what was the Laplace transform of a derivative time domain signal? It was S times X of S, right? It's the same here in unilateral Laplace transform, of course. But now we have an initial condition that must be known, because we don't have the integral of what happened before zero. We don't have any information about that. We didn't accumulate that information in the integral. So whatever happened there stays there, but we have to know what it resulted. It results the initial value of X of 0. So what is X of 0? What's the initial value? It must be given to you. Since you don't know what happened before that, that information must be provided to you. And the second derivative is, it requires even more information. It requires S squared times XU of S. That much is the same, but you have to know the initial condition in time, X of 0, and multiply it by S. And you have to also know the initial condition on the first derivative. This is the second derivative, so what happened to the first derivative at 0 minus? This you have to know. And the more derivatives you take, you start pushing these terms towards more to the left of the equation by multiplying further with S squared, S cubed, etc. It may be a good idea to see what happens to the third one, then I will give you the general form. It will be S cubed X U of S, which is the easy part. Then minus S squared X of 0 minus S X prime 0 minus, which is the initial condition of the derivative, minus X double derivative initial condition. Okay, goes on like that. So in general, the nth derivative not equals, it will give you a unilateral Laplace transform of S to the n X sub U of S minus S to the n minus 1, the initial condition. Why am I writing minus 1 over there? It's 0 minus only. And minus S to the minus 2, n minus 2, X derivatives initial condition, minus all the way up to X n minus first derivative at 0. So all the derivatives up to n minus first derivative must be given, as well as the signal itself at 0. Now I'll be quick about this, sorry, because we're running out of time. Give you a differential equation, d squared y of t by, and since I'm trying to be fast, things started going wrong, dt squared plus 3 dy of t by dt plus 2y of t is equal to x of t. Now, how do we solve these differential equations? Well, from differential equations, you may remember that there are two parts of the differential equation solution. One of them is called the homogeneous part. The other one is known as the particular solution, and the particular solution gives you a result of a particular input, and the homogeneous part is a generic solution with 0 initial conditions, without any initial conditions. Now I realize that it's already 3:50, So actually, I won't be able to finish this question. So I will stop at this point. In the beginning of next week, Monday, I will start with this question. I will solve the differential equation in a way that you are familiar with, you should be familiar with. And then I will stop the recording, which will be a standalone, isolated lecture dedicated to this, to the answer of this particular question. And then I will start the lecture again, continue with the rest of the course. It may be 3 different lectures on Monday next week, but yeah, whatever. So let's not continue with this one because the time will not suffice. It will not be sufficient. So I'm stopping at this point, the lecture. But before that, if you have any questions, I will give you just a few seconds so that you may ask if you're familiar, if you're keen on asking things, if you have anything in your minds. So as you see, things are related to one another. There are differential equations, there's signals and systems, there is circuit theory, there's electronics, there is control systems, there is telecommunications, and then there's digital algorithms. But after all, they're all combined, and you have to know just all the fundamentals. Without the knowledge of these fundamentals, you're in trouble. That's why you are learning all these things. Because in the undergraduate, I was also asking myself, shall we ever be using these things in any kind of an application? And the answer is a big yes, unfortunately. So we will continue from here. As I see no question, I'm stopping the recording now. See you next Monday.